You probably know that you are star stuff. Your atoms were made in some star and found their way to Earth. No atoms are created or destroyed on Earth. We just recycle whatever was given to us. However, have you ever wondered how many atoms that are now part of you were once in Julius Caesar's body? Or how many atoms of those you have inhaled were once inhaled by Julius Caesar too? If you did not know, these questions are classic Fermi problems. They're not elementary problems. Their complexity is higher than the complexity of other Fermi problems. The road to the final answer contains several steps. However, their appeal to our curiosity motivated me to present a solution in one of my first videos. I will work out the problem with the inhaled atoms, which I will break down to small step-by-step calculations, so you can appreciate the beauty of Fermi calculations. Understanding its solution will strengthen your confidence to work on other Fermi problems and help as a template how to partition hard problems in smaller, manageable ones. Towards its solution, let's first see what data you are allowed to use if necessary. 1. Math formulas. 2. Physics laws. 3. Simple data that are supposed to be known. For example, the radius of the Earth, the atmospheric pressure, the atmospheric composition, the atomic weights, and the age of Julius Caesar. The useful data of a problem depend on the question asked. Hence, the data which will be required will be different from question to question. The wider your general knowledge and your mastery of trivia, the wider the spectrum of Fermi problems that you can solve. Now, let's answer the question. How many atoms of those you have inhaled were once inside Julius Caesar's body? Here are the smaller problems we must solve for this question. 1. How many atoms in C did go through Julius Caesar's body during his lifetime? 2. How many atoms in you have you inhaled and exhaled during the period that you have lived? 3. How many atoms in does the atmosphere have? The solution of the three previous problems lead directly to the solution of the question that has been asked. Here is how. Assuming uniform mixing of the atoms, the probability that a randomly selected atom of the atmosphere was once in Julius Caesar's body is P equals NC over N. Then, among the atoms that you have inhaled, the fraction that was in Julius Caesar's body is P times NU equals NU times NC over N. In fact, notice that the second problem is identical to the first problem. Julius Caesar lived 55 years. He actually died about 4 months short of his 56th birthday. Therefore, if A is your age in years, NU equals NC times A over 55. And hence, the answer to the original problem requires only the solutions of the first and third partial problem. NC square A over 55N. We only must compute N and NC. Now, let's compute NC. Towards this goal, we need to compute the number of atoms a human inhales per breath, given that at rest the average adult takes in about 500 milliliters of air per breath. Assuming standard conditions of room temperature, 25 degrees Celsius, and pressure at the sea level 1 atmosphere. The ideal gas law can be used to compute the number of moles of the inhaled air. Then, multiplying by Avogadro's number, we obtain the number of molecules of the inhaled air. And since the inhaled molecules are mostly hydrogen and oxygen, which are diatomic, multiplying by an additional factor of 2 gives the total number of inhaled atoms per breath. It remains to compute Julius Caesar's number of breaths during his lifetime. At rest, a human breathes 12 to 20 times per minute. Assuming a frequency of 15 times per minute, this gives 21,600 breaths per day, or 433,620,000 breaths for 55 years. Multiplying the number of breaths by the number of atoms per breath, we find that 1.067 times 10 to the power of 31 atoms were inhaled by Julius Caesar during his lifetime. The human body also contains 10 to the power of 28 atoms. However, Since they are 3 orders of magnitude fewer than the atoms exchanged by breathing, we can ignore them in this approximate calculation. Now we move to compute the numbers of atmospheric atoms in. The atmospheric pressure at sea level is 100,000 newtons per square meter, and it's due to air's weight applied over the surface area of the Earth. Hence, using the defining equation for pressure and weight and the equation of the surface area of a sphere, we compute the mass of the atmosphere. 5.13 times 10 to the power of 18 kilograms. The mass of the atmosphere can be converted to the number of moles if it is divided by the air's average molar mass. The atmospheric air is a mixture of 78% nitrogen with molar mass of 28 grams, 21% oxygen with molar mass of 32 grams, and 1% other gases. Using the exact composition, we can compute the exact molar mass. However, since we only solve an approximate problem, we will set it to be 29 grams per mole as computed by using the nitrogen and oxygen only. Hence, we find that the atmosphere has 1.8 times 10 to the power of 20 moles of gases. Multiplying by Avogadro's number and a factor of 2 due to the diatomic nature of the gases, we conclude that the atmosphere has 2.16 times 10 to the power of 44 atoms. Knowing NC and N, the probability that a randomly picked atmospheric atom has been in Julius Caesar's body is 5 times 10 to the power of negative 14. Therefore, among the atoms you have inhaled in AE years, AE times 10 to the power of 15 of them have been in Julius Caesar's body. This is an impressive result. Each and every person will share between 10 to the power of 15 to 10 to the power of 17 atoms with Julius Caesar. The calculation can be modified by including various subtleties. For example, the exact molar mass of the air may be used, and in fact humidity may be included too. Or we can adjust for the possibility that some atoms that were inside Julius Caesar's body after they were exhaled became locked inside trees or sediments. However, the order of magnitude of the result will remain close to what was computed. Then it is obvious that selecting Julius Caesar for stating the problem is irrelevant. It is done only for drawing your attention. You share atoms with every historical person, such as Aristotle, Shakespeare, and Jack the Ripper, and even other beings such as dinosaurs and mammoths. In the latter case, the calculation needs some correction due to the different volume of the inhaled air. You are invited to work out the corresponding result. You are also invited to compute how many of the atoms you will inhale in your lifetime have been inside the bodies of 2 historical figures, say Aristotle and Julius Caesar. If you have reached this point, then you have understood all key points of the calculation. The remaining part of the video presents it again in symbolic notation without narration. The symbolic notation allows you to modify the value of any parameter as many times you wish without redoing the entire calculation from scratch. You can skip this part or follow it with your notebook handy, so you check and reproduce the calculation on your own. Are you ready? Let's start.